In this lesson, we'll dive into another powerful machine learning model, the Support Vector Machine, or SVM. SVM is all about finding the best boundary, called a hyperplane, that separates data into different classes. In this video, we'll work through a complex application of SVMs, recognizing handwritten numbers. We'll start by importing the necessary libraries. We're bringing in NumPy for numerical operations, Matplotlib for visualization. In the next cell, we're going to load the MNIST Dataset, which is a collection of 70,000 small images of handwritten digits. This dataset is often referred to as the hello world of machine learning. As we can see from the output, the dataset has been loaded successfully. We've extracted the features and target labels and converted them into integer types. The dataset contains 70,000 images, each with 784 features, which represent the 28 by 28 pixel values of each image. We have 10 classes, representing digits from 0 to 9. Now we're visualizing sample digits from the MNIST dataset. This gives us a good idea of what we're working with. Each image is a 28 by 28 pixel grayscale representation of a handwritten digit. We can see one example of each digit from 0 through 9. We're also looking at the class distribution in the dataset. This bar chart shows the dataset is fairly balanced, with roughly the same number of examples for each digit. This balance is important for training our model effectively. Before training our SVM model, we need to pre-process the data. We're using a min-max scaler to normalize the pixel values to the range of 0, 1. This normalization step is crucial for the SVM performance because it ensures all features are on a similar scale. Now we're going to split our dataset into training and testing sets. We'll use 90% of the data for training and reserve 10% for testing. This will allow us to evaluate how well our model generalizes to new unseen data. The split has been completed successfully. We have 63,000 examples for training and 7,000 examples for testing. In this step, we're going to initialize and train our SVM model. We're using a linear kernel for simplicity, though SVMs can use various kernel functions to handle different types of data relationships. Now we're going to evaluate our model's performance by making predictions on the test data and comparing them to true labels. We'll use the common metrics like accuracy and the classification report to assess how well our SVM model is performing. The results look impressive. Our SVM model has achieved high accuracy on the test data. The classification report provides a detailed breakdown of precision, recall, and F1 score for each digit class. These high values across the board indicate that our model is doing a good job recognizing all digits. To better understand what our model is working with, we're visualizing a sample digit from the dataset. This function reshapes the 784 features back to a 28 by 28 image, and then displays it using a heat map. Here we can see a visualization of the first digit in our dataset. The hot color map highlights the pixel intensities, showing us exactly what the model sees when making its predictions. To visualize the SVM decision boundaries, we first need to reduce the dimensionality of our data. We're using Principal Component Analysis, PCA, to reduce our 784 dimensional data down to just 2 dimensions. This allows us to plot the data and see how SVM separates the different digit classes, while the scattered points represent individual examples. Though keep in mind, this is a simplified representation of the actual 784 dimensional decision boundaries. In this demonstration, you've seen an example of how SVM creates optimal decision boundaries between classes, and are particularly valuable when you need a clear margin of separation between classes.